All right, that was very rude of Zoom, but they kicked us off. So I'm going to start back up. I don't know exactly where it cut me. So what I was saying at the end of the last part, when we dissolve an ionic compound in water, those ions can split apart because we can increase the number of attractive forces that we will experience. So ionic compounds dissociate in water, which means they split apart. So let's try another example. Here we've got sodium nitrate. So if I'm going to draw a particle diagram for sodium nitrate, sodium is Na, it has a charge of +1. We've talked about how to draw a polyatomic ion, which nitrate is. So nitrate is NO3 with a charge of -1. So that's a nitrogen and 3 oxygens, and they are all sharing that charge of -1. So we've said, let's put it in a dotted line, and uh, let's just draw that charge on the inside. So there's a few bonds that are occurring here. There's a bond between sodium and nitrate. That bond is ionic, right? Our sodium has a positive charge, the nitrate has a negative. But then there's also bonds between nitrogen and oxygen, and those are covalent. In this case, we don't really care about polar or nonpolar because this whole thing, again, has a negative charge. So we don't really care if there's any partial positives or partial negatives in it. It just has a negative. So let's see how that would be different. If I dissolve this in water, again, I'm starting off with my solid sodium nitrate. I'm going to simplify a little further. My nitrogen is just going to be an open circle. My oxygens will be closed. This thing has a charge of -1. When I dissolve an ionic bond in water, it will dissociate into the ions. So we would have sodium by itself now. But then here's what's interesting. This polyatomic ion, it still splits, but the covalent bonds on the inside stick together. The reason this happens is because those covalent bonds are made of strong attractive forces, and we can't actually split those apart. So what we're going to do now is we're going to throw our waters in here, and we're going to see if we can predict what water would do. The oxygen side of my water is partially negative, so I'm going to predict that my oxygens would be attracted to the sodium. So I'm just setting a few of them up. There's 3 water particles. Go ahead and fill my hydrogens in. The oxygen is always facing that sodium. On the other hand, the hydrogen side of this particle is going to be partially positive. So if I add a couple more waters in, the hydrogen side of these waters is going to be facing that fully negative nitrate. So again, we see that the ionic bond dissociates, but the covalent bonds do not. So we've got 2 more examples. I would suggest that you pause the video here, go try them, and then come back because I'm going to speed run through them. If we look at methanol, oh, sorry, pause, go try them. That's not a suggestion, that's a do. All right, hopefully you've tried them. If you come back, here's what my particle diagram for methanol would look like. I'm just going to use open circles for the hydrogens. So it should look like that. We have a bond between carbon and hydrogen that's nonpolar. We have a bond between carbon and oxygen that is polar. Electrons get pulled towards the oxygen. We have a bond between oxygen and hydrogen that is also polar. The electrons get pulled towards oxygen. So what we should expect is that the oxygen side of this molecule is partially negative, and the rest of the molecule is going to end up being partially positive. So this is a polar molecule. So if I'm drawing just a particle diagram, here's my carbon, here's my oxygen. Again, I'm just going to use circles to represent the waters. All of the bonds in here are covalent, so we will not dissociate anything. The carbon stays bonded to the oxygen, the hydrogens stay bonded, and we will end up with a structure that looks like this. But then to place our water particles, we have to think about where the partial positives and negatives are. Oxygen is going to be attracted to the partially positive side. So we said that was going to be down here. So if I draw a couple waters in, I'm going to make sure that the oxygen side of those waters is facing the bottom of that molecule. On the other hand, this oxygen in our methanol is partially negative, so I could draw some more waters with the hydrogen side of that particle facing the oxygen because the partial positives and negatives will attract each other. Notice this molecule, number one, does not dissociate. So when we write the formula, we would call this CH3OH aqueous to show that that whole molecule is still together, but now it's been dissolved in water. We do not dissociate, so we don't actually break up into different pieces, but we are still soluble. Now, you might notice this section over here, there's not a whole lot of water surrounding, and there might be a little bit of interaction, but typically what we see is that larger and larger molecules become less and less soluble because it's harder for the water molecule to surround the entire substance. So if I was a guessing person, I would guess that maybe this methanol isn't quite as soluble as the ionic examples we saw earlier. Speaking of, I did forget to write this in. So we dissociated into sodium. So we could say that this sodium ion is aqueous, plus the nitrate ion, which is aqueous. So we've dissolved those individual ions. We can write our formulas like that afterwards. All right, if you have not tried tetrachloromethane, go ahead and pause the video again. Take like 4 minutes to try this. I don't super care about the Lewis structure part. I'm okay with us just drawing particle diagrams, but pause and then come back. Welcome back. Here we go. We got a carbon. It's bonding 4 chlorines, so I would expect it to look something like this. The only bond that exists is between carbon and chlorine. Carbon has an electronegativity of 2.5. Chlorine is 3.0, so this is a polar covalent bond. We would expect electrons to get pulled towards chlorine. But as we look at this molecule, we would see that electrons are getting pulled in every direction by chlorine. So we have a symmetric molecule. If the molecule is symmetric, that means we have a nonpolar molecule. So all those pushes and pulls end up canceling out. Well, what does that mean? That means if we have a CCl4, I'll go ahead and draw 3 of them. There's no spot of the molecule that's more positive or more negative. So there's nothing for our water to be attracted to, which means if we put them together in the same container, the water has no reason to surround the CCl4. In fact, what we would end up seeing is that instead of bonding together, we would form 2 separate layers of our water particles versus our CCl4s. So when I'm done, my diagram would look something like this. We have 1 layer of water, and we have a second layer of our CCl4. This is what we call an insoluble substance. Insoluble means that it does not dissolve. If I were to write the formula here, this would just be CCl4 as a liquid plus H2O as a second liquid. Nothing is aqueous because it hasn't dissolved. Finally, last piece we can say here, if we have an insoluble liquid and we mix it with water, we can use the term immiscible, which now I'm getting worried I spelled wrong. Oh, I got it. Immiscible just means that it doesn't mix. Typically, if we talk about a liquid being insoluble, we can also use the term immiscible. All right, that's all I got for you. Sorry that our video is going to be split up into two different sections, but hopefully you can watch the two of these and feel like you know what's going on when we're trying to dissolve something in water. This should give you a chance to try to work on the dissolution worksheet, which you should get from the sub. As you're doing that, be sure to write down any questions that you have so that you can ask them either in SRT or next time we see each other. Thanks, everybody. Bye.